they say that 66% of animal owners will greet their pet before their spouse. We want to test it out, so we're going to try this on 12 people. All right, Casey, is this a binomial distribution?
Yes.
Why?
Because there's a certain number of trials.
And in this problem, what is the fixed number of trials?
12.
12. We're only going to talk 12 people. We're not going to keep going until we get so many successes or anything like that.
There's only 2 options.
And what are the 2 options in this problem?
That they met their dog before their spouse or after their spouse.
Exactly. They either met their dog before or they met their spouse first. There's only 2 options there. Third one?
They're independent.
Now say this right. I want you to say it right. Yeah, they're independent. Now how do I say this?
One person meeting their dog before their spouse doesn't affect the next person meeting their dog.
That's the best that's ever been said. That's exactly what I want you to do, okay? One person actually meeting their dog isn't going to affect that next person whether they meet their dog first or not. Perfect. And the fourth one?
It doesn't change the probability of the next person.
Right, the probability is always going to stay,
The same.
which is
0.66.
66%. Okay. All right, then you were asked to go ahead and create your probability model for this. I did say, when you're ever asked to do this, I do want you to show the work for one of them, okay? And then you can just use your calculator and obviously take it from there. So on your paper right now, you should have the formula written. Mason, what's that all about, this thing?
That's the probability, or that's choosing,
Why is it there? Why is this thing in our formula?
because that's to choose which, how many you're taking out of the 12.
Why is it there? What does this do in the binomial? Think of the tree we drew yesterday. What is this thing doing? Why is this?
Oh, it's making all the possible ways that it can be.
Like, for example, if I'm trying to figure out, you know, if I'm asked 12 people, I'm trying to figure out the probability that 5 of them would greet their dog first. We drew a big tree for this yesterday. What this guy is saying is how many different ways down the tree are there? In other words, if I want 5 of them to greet their dog, I'm going to have 5.66s. And I'm going to have 7.34s. But they can come in a bunch of different ways down the tree. So that's the multiplication and the addition roll at the same time. So that's there to say how many different ways that can be done. Times the probability for success, how many successes you want. Times the probability of failure, how many failures you want. So what I'm saying is, like, just show me one of those, one of your 13 probabilities. So if we do the one I just talked about, what's the probability of 5 of them choosing their dog first? That would be 12, choose 5. I saw some of you out there with like division signs in here and stuff. Don't. Okay, that's exactly how we write it. Okay, that's the number of combinations of 5 you can choose from 12. Probability of success, 66%. I want 5 of those. Probability of failure, and I want 7 of those. Okay, so just put that on your chart next to the 5, and that's good enough for showing the work on that. All right, fortunately we did learn a pretty cool shortcut for this yesterday. There is a button on our calculator which will do exactly this. Okay, so the button's programmed to do exactly that. It's binomial PDF. So if I go in and I create my probability distribution function, it will start at 0. All binomial problems start at 0. And for this, it could go all the way to 12 different people that choose their dog first. Now get them all done all at the same time. Highlight the top. Go to your binomial distribution function, the PDF. The first parameter is what your fixed number of trials is. Second parameter is the probability for success. And third parameter, we want them to do it for every single possibility there. There we go. Now don't freak out about this. Okay? Think about it. Let's go back to basketball shooting. If someone's a 66% shooter and they shoot 12 free throws, is it very likely they're going to miss them all? Somebody's a 66% free throw shooter, they're going to shoot 12 free throws. Is it very likely in the long run they're going to miss them all? No. I guess it is possible. Okay, remember this is scientific notation, so this is 0.000000246. Now I saw some of you on your pictures drew little rectangles over there. No way. Those things wouldn't even show up. If you drew a little rectangle for this, then this rectangle would go to the moon. Okay, so be very careful with that. And there's one we just did here. Chances of 5, it's 5.21% in the long run of that happening. Okay, I then asked you to create a graph for this. You can do it on the calculator. It's not real easy. I'd go ahead and do it by hand. I would like these separated, however. Remember, this is a discrete distribution. Your book doesn't even separate them. You're going to see the calculator doesn't even separate them, but I want you to think of them as separate. There's only a possibility of 1 or 0 or 3. There couldn't be 2.5 or 2.4 or something like that. So if you keep them separate, it keeps in mind that it is in fact a discrete probability distribution. But there's the picture that you should have gotten for this particular problem. That thing kind of looks familiar. What does that look like? Shh. What does that look like? Looks like a histogram, correct? But any kind of special histogram? Come on now. So I asked this question in the 4th period. You know, they're kind of special. So the person said, yeah, it looks like a hand. Oh, come on. I mean, you guys need to get a committee together and go to the principal and get me fired. If that's all you could come up with after, we've been at this for 4 months. What's that look like? It looks like something. A bigger hand. Does that look like a little bit to you? Look familiar a little bit, kind of? What does it kind of look like a little bit?
Like normal.
Oh, kind of looks a little bit normal. Doesn't it? Unimodal, medium tail, symmetrical. Maybe not perfectly symmetrical, right? Now remember, this is critical. A normal distribution is a continuous distribution. In other words, it's not discrete. They wouldn't be separate rectangles. Okay? A normal distribution, you can get 2.4 and 2.5 and stuff like that. But you're right. You're right. That thing looks like something we've seen before. Keep that in mind a little bit. All right, finally, I asked you to go back to this chart and go calculate the mean, the expected value, and the standard deviation of this distribution. These formulas are on your green sheet. They should be on your paper right now. The summation of the actual values times the probability that they come up. Got to show me 3 of these, okay? So this is 0 times, that's what we did last chapter, 0.000024 plus 1 times 0.000056 plus, finally, dot, dot, dot. Show me the last one, 12 times 0.00683. You don't get the mean. Fortunately, we don't have to enter all those into our calculator. We do have a calculator button that will calculate the mean for us. And that was stat calculate. Put in L1, comma L2. It knows you have a probability distribution function. And you get the answer 7.92, which I saw in a lot of your papers out there. Now remember what that means. In the long run, if you go ask 12 people many, 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 many times, the average number that you'll get out of those 12 is going to be around 8, 7.92. Okay, I also ask you to find the standard deviation. On your paper should be that variance formula. Plugging in 3 of them, take the square root of it, and that comes out to 1.64. Understand what that means. Hey look, typically I'm going to get around 8 of the 12 that say they meet their dog first, but it's not always going to be right around 8. It's going to be sometimes 7, 6, 11. So on average, if I average all those differences from 8, it's about 1.5 people. Okay? Alright, you guys like shortcuts? I've got one for you. In fact, you could figure out this shortcut. I don't even have to give you the formula for this. Let's think about this now. Let's make this problem a little bit simple. Let's say I'm going to shoot 10 free throws, and I'm a 60% free throw shooter. How many do you think I'm going to make on average? 6. You said 6. How'd you get that? What's the formula for that? What did you do in your head to get 6?
It's just 60% of 10.
Yeah, so of means multiply, right, in math? So you're saying just take the n, multiply it by the p, and you can find what the mean would be? Okay? That's exactly true. In fact, you just derived that formula. These are on your green sheets. Go find them. They're on page 4. They're right underneath your binomial formula. Go find them. You don't have to memorize these guys. If we have a binomial distribution, if you've gone through the big 4, yes, 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 we don't have to go make a crazy chart and then do it the way we did in chapter 7. We have a shortcut that'll calculate what this mean is. And the formula for that is that the mean is going to be equal to n times p. That's exactly what Jason just told us. Let's see if it works in that problem over there. So the mean, we always write the formula down, is n times p. For that problem, the sample size was 12 times the probability, 0.66. Does that in fact come out to our 7.92? Plug it in, verify. It did. So nice. That's a nice little shortcut for us. Okay. If you want to calculate what the mean, doing it many, many, many times, what it would come out to, okay, you no longer have to use that formula from last chapter, but it has to be a binomial distribution. If it doesn't meet the big 4, that formula is not going to work. They also derived another formula in your book for that, and that's how we can calculate the standard deviation. You'll see that on your green sheets as well. So let's double check to make sure this one works. The standard deviation, we always write the formula, NP, 1 minus P. So in this problem, it would be 12 times 0.66 times 0.34. Verify that that does come out to the 1.65 number that we got. So make sure you do standard deviation, use your parentheses correctly. What's that? Yeah, 1.64. Okay? So when we have a binomial distribution and we know NP, we can calculate the mean and the standard deviation from that distribution really quickly. All right, let's go back, James. There seemed to be a little bit of a consensus out there that that thing did look, in fact, a little familiar. Okay, and it looked like a normal curve. Now, what we're going to talk about now, I think was a really big deal before these calculators were invented. Because what statisticians did, they had those normal curve, they had those charts and stuff, and they said, hey, I know this is a binomial distribution, I know it's discrete, but the funny thing is that when I drew the graph of it, it looked like a normal distribution. I wonder if I can use those tables to kind of get me probabilities of things happening that would be very close. And the answer is yes. Quite often these binomial pictures do take on a normal shape. Quite often they don't. Turn your book to page 451. Is anybody going to confuse that graph on the bottom with looking like a normal distribution?
No.
No, that doesn't look very normal at all. It looks very right skewed. I'm not going to be able to use those charts at all for that one. So the question is when do these binomial distribution problems look normal and when do they not? Has anybody got any guesses on when these pictures are going to look a little more normal? Yeah.
When the 50th percentile is right in the
Yeah, if the mean is in the middle, that P is 0.5, I agree. Okay, it kind of looks like that it would start in the middle and it would go down symmetrically on both sides. But I'll tell you this. Let's say your probability was only like 10%. Well, if you do a big enough sample size, even though it's all the way over here as the middle, it will normalize. Because these probabilities will get so small. You know how these got small, you won't even see them anymore. So if you have a big sample size, or that probability is in the middle, this picture is going to look like a normal curve. So somebody, a lot smarter than me, figured out kind of a good test for you. Okay, and this is our test. If both n times p is greater than 10, and n times 1 minus p is greater than 10, then your picture is going to look like a normal distribution. If either one of those doesn't work, it's not. And you bet you can't use those tables to get close. So let's try this test out and see if they both work. If they both work, I can draw this thing. If they don't work, don't draw it. So let's try it on our warm-up problem. So, as always, we always write down the formula, then we plug in the numbers. So we're going to test out np and n1 minus p to see if it's greater than or equal to 10. Let's plug in the numbers. The first one was 12 times 0.66. That one was, 7.92. I already know that I shouldn't be drawing a normal curve. Even though, what did the picture looked pretty good, didn't it? Doesn't the picture we drew look pretty good, but still not good enough? Remember, we did see a little bit of skew going on in that picture. Let's just try the other one for fun. So this is 12 times 0.34. I think this is 4.04. The bottom line is there's no way that they're greater than or equal to 10. Yeah?
Are we multiplying it by the n and p?
No, it's just the formula is, you do two different calculations. The first one is we're going to multiply n times p.
Oh, for that test. Okay.
We're doing this test. We're seeing if we can use this thing called the normal approximation. Didn't work. So let's change the problem around. Let's increase the sample size a little bit. So let's say instead of checking out 12 people, okay, we're going to sample 1,200 people. Okay? And then here's the question that I'm going to ask. Now, like I said, we have calculators that do this. We're going to do it on our calculator first, and it's going to be the exact answer. So I think they developed all this stuff before we had the calculators that we have. I'm going to ask 1,200 people. I want to know the probability that at least 800 of them are going to go to their dog first. Okay, so that's the question that I'm asking. So the specifics of this, n is 1,200. Probability for success is 66%. Okay, I want to figure out the probability that greater than or equal to 800 of those people are going to go to their dog first. All right, you guys did this problem last night. How would you do this on our fancy calculators? This would be what? The probability of 800 plus the probability of what? 801 plus ... all the way to the probability of 1,200. Did we do this last night? You would write the formula, you would plug the formula in for them, but I'll let you use our fancy calculator button right now. How would we figure this out real quick with our fancy calculator button? This would be, this last night, figuring out 800 or more is 1 minus, what calculator button is that? CDF, 1,200, 0.66. What would go here? 799, right? That would add, the CDF adds up all the way from 0 to 799. Take 1 minus that, it's going to leave the 800 and on. Go ahead and throw that in your calculator, see what percentage we get. Now remember, I never want to see this on your paper. The CDF function adds up 0 all the way to you tell it to.
Point 325.
0.325. So in the long run, okay, if you ask 1,200 people about whether they visit their dog first or not, there's about a 32.5% chance that 800 or more of them are going to. Okay? This is the exact answer. Okay? Precise answer. However, if this meets this criteria, this problem meets this criteria, we can also solve this problem a different way. We can draw a normal curve, fill in, do our shading, get our z-scores, and go calculate this percentage as well. Now, the one we get from the normal curve is called the normal approximation. It won't be precise. Why? because we've gone from a discrete distribution, we've changed it to a continuous. It doesn't match up perfectly, okay? But we can get pretty close. All right, so I want to do the same problem, but now we're going to use the normal approximation. What's the first thing that we should do? What's that? Write the formulas. Okay, see if we can draw the normal curve or not. You can't draw that curve unless it passes these criteria, which remember our first warm-up didn't. Couldn't do the normal approximation for this. So let's see if that works. Okay, so NP is what I'm going to be looking for tomorrow on your homeworks. What is N? It's 1200. Probability for success is 0.66. Plugging that in our calculators, you need to show the numbers that you get here. And I think that's going to be 792. That one sure was okay, right? That's more than 10. Okay, check the other one out. 1200 times 0.34. What does that one come out to? 408. All right. Yes. Yes. Big check mark. They both were more than 10. Why do I do that? If I put that picture up on the wall just like we did for that problem, boy, it would be really looking nice. That's what that tells us. So therefore, let's solve this problem using the normal approximation. This is the problem you've done 100 times already. So what do I have to do first? What do I label on here first? The mean. What's the mean? N times P, right? We have a formula for that. In fact, in this process that we did here, we did N times P, didn't we? So you can kind of see it here. That's one of the things that we did. So 792 goes here. I'm looking for the probability of greater than or equal to 800. Okay, put 800 here. I shade it. What's my next step?
Calculate z-scores.
Gotta go get my z-score. So let's write our z-score formula. You guys did a nice job on your last test on this. Pretty much everybody was pretty solid at this. All right, let's plug in the numbers. So this is going to be 800 minus 792 divide... Uh-oh. I need the standard deviation of this distribution. Yeah.
You already solved it.
No, I didn't.
Oh, wait, no, you
No, I didn't. I have not solved it yet.
can solve it.
You can solve it. How?
Use that one.
Yeah, remember we got the formula here. That's why they gave it to us. Okay. Now you could write it over here and go get the decimal, but if you want to just put it all down here right now, that's okay too. Okay, so this is going to be 1200 times 0.66 times 0.34. Go see if you can get that whole thing into your calculator and go get the correct z-score. How many standard deviations away is 800 from 792? Some of you lost points on your last test because you didn't go fill out your table fully, your picture fully. About 4.9, around 0.49. I think that's correct. Okay, so it's about half a standard deviation away. What do we do now? Go to our tables. Go to your tables and go find the probability of the shaded region. Now it should be pretty darn close to the right answer, which was 0.325. Looking up a z-score of 0.49. What do you got?
0.6872.
That's not close to 0.325.
Subtract.
Yes, very good. What you found is right. What did you say? 0.6872? Is that what you said?
Yes.
So over here, that would be 0.3128. This is the normal approximation to this problem. Okay? And this is, I think, all they had before we had on CDF. But we could actually find the exact answer. Back in the day, this is what they had to do. They said, hey man, that picture kind of looks normal. I can work this out. We'll find out how many z-scores that is away and get an approximation to the right answer. I think you do a couple of problems tonight where they want you to do both. And then they want you to tell how far the distance was away. Just subtract these two and you got it. Okay? All right, normal approximation to a binomial distribution. First of all, we learned how to calculate the mean, the standard deviation of a binomial distribution. Make sure it's binomial, or don't be using these formulas. Okay, these are formulas for only a binomial distribution. Definitely can use those to help us to calculate the normal approximation.